Good morning. In the last class, we have learned the Maxwell's equations and the derivation of these Maxwell's equations using the thermodynamic potential relations. That is, the thermodynamic potential relation for infinitesimal processes using a mathematical theorem. Today, and you can see that there are different variables. Each Maxwell's equations contains different variables, that is the partial derivative at constant pressure, some is at volume, entropy, pressure, etc. So it is very difficult to remember, and if once you get all these thermodynamic relations, that's potential relations, you can find the Maxwell's equations very easy. So in order to remember these thermodynamic potential relations, there is an easier way to remember the thermodynamic potential relations for infinitesimal processes. It is a diagram, and that diagram is known as conic bone diagram. Conic bone diagram. This is also known as VAT VUS diagram. VAT VUS diagram. So using this diagram, it is very easy to obtain the four thermodynamic potential relations. So what is a VAT VUS diagram? So the VAT VUS means the left corner is V, then on the top VAT, here VUS. VAT VUS diagram. It is volume, this is Helmholtz function, temperature, internal energy. So these thermodynamic potentials are written in the center of each side. So here we can write this is actually G and the remaining is H. The different thermodynamic coordinates are written on the corners, that is temperature, volume, entropy, and remaining is pressure. So this is VAT VUS diagram. The remaining is G and H and the P. So thermodynamic coordinates are written on the edges of this rectangle or square, whatever it may be, you can draw like that. Then the thermodynamic potentials are written on each center of each sides. So there are two arrows also. One is the arrow from P to B, and the other is from S to D. This is the VAT VUS diagram. So each represents, each thermodynamic potential is a function of two variables. Each potential is a function of two thermodynamic coordinates or variables. So you can see that here U is in between V and S. The U is written or U is marked in between V and S. So U is a function of V and S. So you can write U is a function of V comma S and A is a function of V and T. Then G is a function of T and P. Then H is a function of S and P. So this one we have already derived earlier, the dependencies of each thermodynamic potential on the thermodynamic coordinate. So from this diagram it is very easy to write this dependency or the dependency of each thermodynamic potentials to the thermodynamic coordinates. That is, U is a function of V and S, A is a function of V and T, and G is a function of T and P, and this H is a function of P and S. The first thermodynamic potential relation is for D. So we can say that U is a function of V that we have to obtain from this VAT VUS diagram. That is, u is a function of v and s means there is a change in u depending upon the change in volume and s that we have written here. So, what is the coefficient of ds or coefficient of this quantity? For that, there is an arrow connecting the conjugate. This is known as the conjugate variable here. For this s, this is the conjugate one. For v, this is the conjugate one. This is the connected one. So, for finding the coefficient of s, we have to just look. We have to just know what is the conjugate connecting for this s. What is the conjugate coordinate here? S connecting to t. So, we have to, we can write the coefficient of s by observing the conjugate coordinate, that is t. So, for ds, the coefficient should be t. So, each coordinate is connecting from the differential coordinate to the conjugate coordinate. From the differential coordinate to the conjugate coordinate. So, here from s to t, so we can write for ds as t. The next one is for dv. So, we have to look at v. What is the conjugate connecting from v to p? From v to the conjugate coordinate. From v to the conjugate coordinate, this is p, but this is in the opposite direction. That is, we have to find from the conjugate, from the differential coordinate to the conjugate coordinate. So, here the arrow is in the opposite direction, that is from the conjugate to the differential coordinate. The differential coordinate is dv. So, from this we have to find, we have to observe from the differential coordinate to the conjugate coordinate. Since this arrow is in the opposite direction, that is from here to here, we have to write a minus p. So, this is the first thermodynamic relation, thermodynamic potential relation. So, just have a look at the h. We can write h similarly. So, h we have written that h is a function of s and p, because h is in between p and s. So, we can write like that. So, h is a function of s and p, or p and s means there is some value of ds and some value of dp. So, next we have to find the coefficient of these variables. For that, we have to have a look at the conjugate coordinate from the differential coordinate to the conjugate coordinate. That is TDS plus VD. Like that, what is the third one? Third one is dA. Since A is a function of V and T, so dA should contain a term of dV and a term of dt. So we can find the coefficient of this dV and dt. How we can find the coefficient of dV and dt? So we have to find from the differential coordinate to the conjugate coordinate. Here from the differential coordinate to the conjugate coordinate is minus p, since the arrow is from here to here. We have to observe from here to here. So here this arrow is in the opposite direction. So the coefficient of this differential coordinate or differential coordinate is minus p. So for v we can write minus p. Similarly for t, from the differential coordinate to the conjugate coordinate. Here also the arrow is in the opposite direction. So from s to t. So we have to find the differential, we have to find the conjugate coordinate from the differential coordinate. Here differential coordinate is t dt. So from this coordinate, from this to the conjugate coordinate means here it is the arrow is in this direction, so we can write minus. So minus PdV minus SdT is it is the relation for this Helmholtz free energy. This is internal energy, this is enthalpy, and this is Helmholtz function or Helmholtz free energy. Similarly, just have a look at the fourth thermodynamic potential, that is G. So dG can be written as, what is dG here? dG, it should contain P and P, that is G is a variable of P and P, or G depending upon the coordinate T and P. So it should contain dt and dP. So G should contain dt and dP. So next we have to find the coefficient of dt and coefficient of dP. For that we have to find from the differential coordinate, that is dt here, from the differential coordinate to the conjugate coordinate, the arrow is in this direction, so we can write minus s. So minus s dt. The next one is this one, that is P. So from the differential coordinate to the conjugate coordinate, that is from here to here, that is the same direction. So for this differential coordinate, that is dP, the coefficient is plus V. So it is very easy to obtain for thermodynamic relations or potential relations for infinitesimal processes using this VAT VUS diagram or conic bond diagram. It is very easy to obtain the four thermodynamic relations. To derive these thermodynamic equations, you have to use the dependency and all. You have to differentiate this H. We have H is equal to U plus PV relation is there. So we have to differentiate H, then DH you will get, then U plus PV you have to differentiate. Like that you should obtain the thermodynamic potential relations if the derivation is asked. Otherwise you can use this VAT VUS diagrams. So if we need to remember these equations, you can use this VAT VUS diagram or conic bond diagram directly. So this is the one way to remember this potential relation. So once you obtain this potential relation, you can use the mathematical theorem, that is dou m by dou y at x equal to dou m by dou x at y for obtaining the relation, that is some dz is equal to m dx plus n dy. So we will get the relation that the dou m by dou y at x is equal to dou n by dou x at y. Using this relation, so this is the similar equations. So using this equation and these two equations, we can obtain the Maxwell's equation from each of these equations. So that is all for now. We can learn the applications of Maxwell's relations. That is, we have three TDS equation. That is one of the application of Maxwell's relation. That is TDS relations. That we will learn in the next class. Now we can stop. Thank you.